And in this first week of lab, we're going to focus on just a single degree of freedom system, which is a single mass suspended by a spring damper configuration. So consider like this single story from a two-story building model, which we'll actually study in the second week of this lab. On this system, we put an accelerometer on that moving mass to measure acceleration. We give it an initial condition because the mass is displaced, and we study the unforced response. This lab setup uses a flex sky design, so we get essentially this level lateral motion, as you can see. So we're going to be focusing mostly on unforced response in this lab. Again, only giving initial conditions, but note that the accelerometer, which we'll see is also a mass spring damper system, works by forced response of its base. And we'll talk a little bit more about that in the accelerometer lecture. A follow-up lab will introduce an additional degree of freedom by studying a two-story building model, so we can see what it takes to model and analyze systems with multiple degrees of freedom. So what I'm showing here are two different configurations that are helpful to think about in the context of this couple of labs that we're going to have here. One we can call a fixed base configuration, which is the most common one that you're probably used to seeing in different classes. You have a fixed base here, and note I'm showing the constitutive laws. Like for this spring, if we assume that it's linear, the stiffness relates the force on the spring to the displacement of the spring, and also a damping parameter, B, relates the force on the damper to the velocity of that damper, which is the relative motion of the two ends. And then we have momentum, linear translational momentum related to the velocity of that mass. So this is a very common mass spring damper system that you've seen in many contexts, and again, very useful in modeling basic structures and so on. The other is a base excited configuration, and this is a little different. In this case, well, coming back here to the fixed base configuration, I'm showing that there's a force applied here, and that might be something of interest, right? We want to know how this system might respond to different forces that are placed on here. In this case, when you have base excitation, while you could have a force on the mass, and of course you could have gravity acting on the mass, what's happening now is that the base is excited, so that's a little bit of a different configuration, right? As opposed to the a fixed base. This is a model that you might use for, say, modeling a vehicle suspension. The base here, you would have a model of that moving over the ground. Also, most seismic sensors, which an accelerometer is one class of, this is a model for different types of seismic sensors, whether they're made for measuring velocity or acceleration, which is the case for accelerometers. Again, whenever you'll see the values K and B given as here, we're making the assumption that those elements are modeling materials or components that have linear constitutive relationships between the forces and their respective parameters, in this case velocity or displacement. Okay, and that's something that you will have seen in your dynamic systems class, for example. Okay, so now let's look at the model for the fixed base mass spring damper system. That's the fixed base configuration. And this, I'm assuming this is a pretty well-known model to you. I mean, something that you've seen, like I said, in physics classes and dynamics and so on. So I'm just reviewing the derivation of that using Newton's law. Usually you apply, right? You apply a free body diagram here, and mass times acceleration is the sum of the forces. So you've got your damping force, stiffness force, and then your applied force. So at the end of the day, right, you get this very familiar second order linear differential equation, right? And it's linear because we've assumed linear damping and linear stiffness, and the force here is an input. What I want to convince you to do is to get in the habit of putting this into standard form, right? So you just divide here by the term on the x double dot term here, and it allows you to define the second coefficient, which is the parameters in front of the x dot term, as 2 zeta omega n. That's by definition. And then the term in front of the x term, the term that's not going to have a derivative, is always going to be your omega n squared, right? So that whatever parameters you have thrown into here is always going to be equal to omega n squared. So omega n is the square root of k over m for this very conventional model. But any system that you model that comes out linear second order ODE, whether it's mixed, fluid mechanical system, electromechanical system, etc., it's very convenient if it's linear for you to put it into this form, because then you can recognize, what is the damping ratio? Because once you have omega n in terms of these parameters, then you can jump over here and you can find what zeta is in terms of the physical parameters, and that's why this standard form is very helpful. We also typically will make the input, here we also divide by m, so you can see actually it should have the same units, right, as the x double dot term. So if this is displacement, that's acceleration. So the input is acceleration. You see, okay, hey, yes, u is f over m. So again, all that, just whenever you're writing your equation in this form, make sure you have units, consistency, and everything's correct, and so on. And then you can just define your omega n. Oh, that's here. Zeta. Oh, I pulled that out of here. And note also that when you have omega n, then you also know what the natural period is. And note, this is undamped natural frequency, and this is the undamped natural period. In a little while, we're going to talk about the damped period, and it's important to keep track of all these because they're distinct, and especially when you start measuring things in the lab. Okay, so again, here's your standard second order ODE, and it's hopefully similar to something that you've seen in your systems class. Now, before we move on and look at other cases, it's very helpful to think about the undamped case. Let's throw away all the damping. See, I've redrawn it here and erased the damper from here. And so now I just have a mass spring system, and this is the very simple case. The ODE is right here, right? There's no x dot term. So we sometimes refer to this as a nice little linear oscillator. You still define that term right here as omega n squared. So whatever, again, physical parameters you have in here, that's going to define your natural frequency, your undamped natural frequency. The nice thing about this equation is, it's got a really nice, solution. And oh, sorry, no, it's also I'm looking at the unforced case here. So I made f equal to 0. So this is the solution for the unforced case with initial conditions. And so you see if x naught is some initial displacement, so let's say I deflect this with some value and release it, then this is if x dot 0 is 0, then my solution is just a cosine. I'll show you that in a second. So you need to know two initial conditions, right? Second order ODE, so you need to have two initial conditions. If this is a mechanical system of this sort, then x naught is a displacement, x dot 0 obviously is initial velocity, right? So again, this is useful because you can apply it to a lot of systems that might have this model equation that's a simple oscillator. Define the natural frequency, and I'll show you some examples shortly. And then you know a lot. It's also this is the case not only for it's very rare to have no damping, but you could have very, very small damping, and you need to verify that your zeta is very close to 0, and then you can simply apply this equation, right? And so here's what that looks like. And I refer to this as this is undamped harmonic motion because it's a single frequency motion, right? Harmonic. So let's say you were to take this little mass spring system and you displace it, right, and let it go, then the solution tells you that there's no x dot term here, right? It's 0, so it's just a cosine. So you get a nice cosine function. And if you know, in this case, K and M, your stiffness and mass, you know what that frequency is going to be. You know what that period is going to be. Or flip it around. If you don't know K or M, you have a system, you deflect it, you measure this period, and that gives you a measure of the natural frequency. And that's, for physical experiments, that's what I'm trying to get you to do, is to recognize that, hey, if I can model this as a second order, using a second order ODE, I can use what I understand about the response to design really simple experiments in the lab and extract the parameters from dynamic experiments like, this way. The other nice thing about this experiment is if you release it with a known deflection this way, then it's easy to estimate other variables. So if this is the displacement, because that's the solution of the ODE, simple derivatives, right, give you peak velocity and peak acceleration, right? So this term here, just by differentiating this, so that means if I deflect it with a known value, I can predict what the peak velocity is going to be, what the peak acceleration is going to be, because I will know what the natural frequency is, right? Again, turn it around. If I measure the acceleration, right, measure the peak acceleration, I can go backwards and measure peak displacement, right? So these are very useful little vibration relationships, the most simple ones, actually, that you can use sort of and keep in your toolbox, and it's things that are easy to remember and to apply in the lab. Right? You'll notice that I've left out the gravity, and what happens is if you have linear vibration systems, at least for those cases, the only thing that gravity is going to do is put the system at a different equilibrium, right? It'll make the mass compress the spring, but if you have a linear spring, you have linear damping, all that's doing is changing the point about which something might vibrate. The effect of gravity and that equilibrium becomes especially important if those springs aren't linear, and then you have to worry about how where you operate, and that the fact that the stiffness varies in a nonlinear manner. So these linear relations that we've been talking about won't necessarily hold, right? Gravity, when I talk about accelerometers in a related lecture, we'll talk a little bit about the influence of gravity and the role that plays in the basic accelerometers. All right. So bottom line is, if the system's linear, use gravity to find where the system sits, so to speak, what the equilibrium is, and then all these linear relations hold about that point. Again, if you're not linear, then you need to follow other approaches, maybe use simulation as an alternative. Okay, so now let's consider the damped cases. Again, I'm assuming that you've seen this in other courses in physics and your circuits class. These second order systems are familiar. You always study this, right? These are second order ODE. Okay, the solutions are classified by the damping ratio, and you recall that, oh, if I find, and as I showed you, you put your model into the standard form, you solve for that zeta, that tells you what kind of solution you're going to have, right? If zeta is less than 1, we call that underdamped. If zeta is 0, obviously it's undamped. If it's greater than 0, that's the overdamped case. When zeta is equal to 1, that's critically damped. In each of these cases, the undamped, which we've already shown, underdamped, overdamped, and critically damped, all have different solutions for this simple linear ODE with constant coefficients, right? I'm not going to go through those derivations. Again, this is something that typically you will review in system dynamics or vibrations class, circuits class. And as I mentioned, some of the excerpts of chapters I put from books put on the course log, you can find some of those derivations if it troubles you not to have them in front of you. We're just going to look at the application really of just the one case of the underdamped case. And because that's going to be the system that we study in lab. So for the underdamped case, right, zeta less than 1, and this is again the unforced case. We're looking at just the response to initial conditions, right? I'm giving the mass, displacement, I'm deflecting the spring, for example. So I've got an x naught. And then I'm also allowing to give initial velocity. It's a little bit harder to specify if you think about it, to know exactly what the initial velocity would be. So a lot of times we'll say we release it from rest and then this guy is 0. But the solution, right, the exact solution is known. By the way, I say here, this is the solution here, x for zeta values between 0 and 1. Actually, it includes 0 because if you were to make this value x naught 0 equal to 0 and zeta equal to 0, this defaults to the undamped case that we've looked at already. So this should include 0. And so note you have in front of the whole this sine and cosine, you have this what you recognize as this decaying exponential with time, and it depends on zeta and omega. And that's why we put so much emphasis on finding these values, because once we find them, then we know everything we need to know about the system. Give it initial conditions, and now you've got the solution. You don't have to run a simulation. And if you have these values well defined for your system, you don't have to run experiments. I mean, that's the whole point. Of course, we'll run experiments in the lab just to verify or to show how well can we find these, how well can we specify them. The other important parameter is that now, in the underdamped case, we're defining a new natural frequency, and this is the damped natural frequency. And look how it's related to the undamped natural frequency. It's related through this zeta, 1 minus zeta squared term. So if zeta goes to 0, oh yeah, so that's just an undamped case. But zeta then is obviously making your frequency smaller, right, for the underdamped case. And this also defines the damped period here. So make note of those two terms. And recognize that when you go into the lab and you've got an underdamped system, these are the parameters that you can measure. You can measure the damped period from a signal, say from an accelerometer, right? You can't measure the natural frequency, and we'll talk about that shortly. I can show you a real simple little VI I put together in LabVIEW. So all I did was put that solution in here into this is a math script node, and I put in how many cycles I want to look at, but I can put in the natural frequency, zeta, and initial conditions, and in a little math script just calculate x here and plot out x over t, and it's really just for purposes of illustration, so you can see, well, here, look, here's, it's running now, right, with my damping is 0, so zeta is 0, it's indicated here. Natural frequency is 1 for these values I've put in here of omega n equals, well, actually I'm specifying those values and specifying zeta, right? So then you can play with zeta, and you can see as I increase the damping, you can see that as I get closer to 1, I get very little, this is called overshoot here, right? I'm releasing it with an initial condition of 1, no initial velocity, and the system's coming back to 0, to the equilibrium. And there's actually a value I want to show you here, value of about 0.707. It's hard to get here, but sometimes that's, there it is, close. 0.707 is a special value. It's the value of damping sometimes used for design of a system like this. It gives you the minimal overshoot and no oscillations. You see that? Once you, and also it's the fastest kind of time to get to that value. Once you go above that, it's a little slower, right? You get less overshoot, and finally you're almost over damped. And actually, if it's less than 0.707, you can get there faster, but then you've got oscillation. So that's why 0.707 is kind of a special value. And of course, you vary natural frequency here. You can see the influence of that. my time scale is changing, so it doesn't look like it's changing, right? So that just shows you sort of the undamped solution. And again, keep in mind that the damped natural frequency important parameter that we actually can measure, and it's dependent on both the natural frequency and the damping ratio. So we need to figure out a way of measuring these, and that's what we'll talk about shortly.